stage for this session on human. Great, great, important topic. So, what is the future of design? Or more importantly, how can we design the future? Artificial intelligence is not making us less human, but more so. Our program today will be dedicated to the delicate relationship between machine and the human experience. So today, I'm very, very pleased to introduce our lecturer, Mario Carpo. Mario Carpo is professor of architectural theory and history at the Barclay School of Architecture at the University College London. His research and his publication focus on the relationship among architectural theory, cultural history, and media and information. I've been the purpose for very important book, actually very important book to me. Two of those books, like The Alphabet and the Algorithm, or lately the second turn, digital turn, are very, very meaningful, and I wanted absolutely to have you to have a glimpse of what it's all about. Design beyond intelligence. So Mario Carpo's thesis is that the user shifts with the tools, and that the current second digital turn in architecture and design today is changing dramatically the way we're thinking, away from the organic logic of our mind. And in the age of experience, today, we are embracing generative tools, and there is really a need for the reinvention of this relationship between human and machine, to consider the balance between rules and norms and the poesy of the human creativity. To discuss this topic, please welcome on stage Mario Carpo. Yeah.
Thank you for this generous introduction, for the invitation. Can you hear me? Can you see me?
Yes.
Good. Because now I'm going to change my glasses to see the screen, so I will not see you anymore.
The same issues as I have. I have to always do with, without.
And now I don't see the audience anymore, but the audience can still see me, right? Good. That's the important thing.
And we are listening.
Good. So, we generally think that computers are machines. And so we tend to think that computers are similar to all the machines we know. We know machines, computers are machines, more of the same. Wrong. Computers are a new kind of machine, a machine which is quite unlike any other machine we have ever seen since the beginning of the Industrial Revolution. If you use computers to make stuff as tools to produce physical things, computers make things following a technical logic which is the opposite of that of all the mechanical machines which have marked the history of the Industrial Revolution. And if we use computers to think, or something similar to thinking, to solve problems, computers solve problems or think following a logic which is the opposite of the logic of modern science, the logic of the science of Galileo and Newton, science we all studied at school. The very same science we use to design and build computers, oddly. This is somewhat counterintuitive and requires a couple of examples of illustration and explanation. For example, this is the first mechanical machines of all times. At the end of the Middle Ages, Gutenberg's printing press. It illustrates in a more transparent way the technical logic of all mechanical machines that would follow. To print with Gutenberg's press, we need to make a mechanical matrix, a metal plate, which when with a press, we used to reproduce identical copies. To make that metal plate, which is the original, the matrix, we must use a lot of material. It takes time, costs money. So once we have made that mechanical matrix, that metal plate, we would want to use it more than once. Because if you use it only once to make just one copy, that copy will be very expensive. If you use it twice and we make 2 copies, each copy will be half the cost. We spread the cost of a matrix over many copies. We amortize the cost of the matrix by making many copies, which gives this diagram. If you see the first lot, when you make just a copy, assuming the matrix costs 100, that one copy will cost at least 100. If you make 2 copies, each copy will cost 50. If you make 4 copies, each copy will cost 25. If you make 10 copies, etc., etc. What does that mean? The more copies you make, the cheaper each copy will be. This is the logic of mass production, which achieves economies of scale through the standardization of the product. Identical copies, make more, they become cheaper. This is what Henry Ford understood when he started to build the assembly line for making the Model T Ford in 1909. This logic still applies today. Metal plates are printed from a mechanical matrix. You want to print more of them to make them cheaper. The more copies you make, the cheaper each copy will be. This is the technology I used to print when I was in high school, to print, tracts or little school documents. It is called a cyclostyle in English and a ditto machine in American English. It's a mechanical machine. It has a mechanical matrix on a drum. You turn the crank, you make a copy by contact. Making the matrix, I remember that from my own personal experience, takes time, costs money. You want to turn the crank gently and delicately so that the matrix will not break and you can use it to make more copies. Mechanical logic, standardization, mass production, economies of scale. The more copies you make, the cheaper each copy will be. Compare with this. Typical cheap laser printer, like the one I have at home, costs 99 euros when you buy it new. You have to replace the toner. The toner is 89.99. You know why that happens. It looks like the printer we have just seen, but if you open it and you look inside, there is no mechanical matrix in it. There is just a laser beam. The laser beam is scanning each line and leaving dots. Each dot is a pixel. And each line is individually printed. I don't know how many pixels you find in a normal A4 page, between 10 million and 100 millions. But when the page is printed, when you print another one, the process restarts from the first dot. The machine has no mechanical matrix to reuse. So if you make a new identical copy or a different one, it will take the same time, it will cost the same money. Making more copies will not make them cheaper. You can print 100 identical copies of the same page or 100 different pages, they will always cost the same. Move to a CNC milling machine, as it was a standard machine in all the schools of architecture 15 or 20 years ago. And you know how it works. There is a drill which is carving the surface of a plate, which is generally timber or some cheap material, and it carves. It is a subtractive technology. Assuming that you carve that surface, which is 1 meter by 2 meters, something like that, it takes 20 minutes, costs $200. You print that panel, you like it, you want to make another one, the same. There is no mechanical matrix. The process will be repeated identically. It will still take 20 minutes. It will still cost $200. If you print 10 identical panels, each panel will still cost $200 because the machine will still take 20 minutes to print it. There is no mechanical matrix to reuse. There is no economy of scale in making more copies of the same original. Every copy, in a sense, is a new original. It is a series of one, always. All the time. 3D printing. This is a statuette. It's printed out of nothing, almost like by magic. Takes 10 minutes, costs $10. And assuming you print a statuette, someone you like, Fidel Castro, Che Guevara, something like that, and you want to make 1 million identical statuettes, and you will think that if you make 1 million, at the end they will be cheaper. No. They would be cheaper if you were using a mechanical matrix, a stamp, a cast, a die, a mold. But you're not, because each new statuette is printed anew from nothing. So no matter how many you make, they will always cost the same. Making more of the same will not make anything cheaper. Standardization no longer saves money. Variations no longer cost money. This new technical logic has a name. We call it digital mass customization. Mass customization, if you think of it, is an oxymoron. These are two terms which should not be together. Mass comes from mass production. That's what a factory does. Economies of scale. Customization is what an artisan does. There are no economies of scale in an artisanal process. So if you mass produce, you do not customize. If you customize, you cannot mass produce. That was the case until the digital came. With the digital, we can mass produce and customize at the same time. We can mass produce variations at no extra cost, which is the opposite of what the industrial world always did. This is a complete reversal of the principle, of the foundation, of the basis of the industrial world as we have known it since the Renaissance until 20 years ago. Let me illustrate that with an example. In the old system, the industrial system, if your business is making teapots and you want to make a good, cheap teapot, you should first standardize the teapot and have the model of a universal teapot. Then you build a huge factory somewhere. You concentrate the production of all the world teapots in one place, say in Mongolia. And in Mongolia, you build the huge global factory for the global world universal teapot. Bigger factory for maximizing economies of scale. And then you need a vast market to be able to sell all those teapots. Bigger markets for cheaper goods. Bigger is not better, bigger is cheaper. A bigger factory makes cheaper teapots. A bigger market allows you to sell more teapots, hence to make them even cheaper. Bigger market for cheaper goods. This is the permanent quest for scale, which the industrial world has been pursuing for the last 250 years. This is the past, because the future is a fab lab, a small participatory digital workshop at the corner of the street. It will make one teapot where you need it, when you need it, as you need it, on site, on specs, on demand, at the same unit cost. It will not be more expensive than the global teapot made in Mongolia. Customization no longer costs more. Standardization no longer costs less. Mass production no longer saves money. Customization no longer costs additional money. This is what we call the flat marginal cost society, because the line, which is the diagram of the marginal cost, is flat. The permanent quest for scale, bigger is cheaper, which was the mantra of the industrial age, is no more. We are moving from a universe dominated by the quest for scale to a future world dominated by the idea that scale is irrelevant, from economies of scale to a new economy without scale. This is not for today, but this is for tomorrow, and this tomorrow is as soon as digital technologies spread and are universally adopted, this new technical logic will replace the old one, the one which we have pre-installed in our mind because we think it is a timeless, universal, inevitable condition of production. Not true. This is specific to the industrial world. Did not exist before the Industrial Revolution, will not exist after its demise. This is just a parenthesis, a blimp on the history of humankind between 750 and 1999. It was important back then, but now it's over. Chapter 1. Chapter 2, if you use computers not to make stuff, but to think, as thinking machines, machines that solve problems. These are the kind of terms that you find discussed: big data, brute force computing, cellular automata, machine learning, deep learning, artificial neural networks, convolutional neural networks, blah, blah. Many of these terms are just a tiny little bit bombastic, and they may be a tiny little bit misleading because they promise more than what artificial intelligence actually delivers. Artificial intelligence is just problem solving. But it is problem solving with a tweak, because machines solve problems very effectively in a way which is different from the way we would solve the same problems. Example. What you see on the left is the way we typically notate a curve. Calculus was invented in the end, at the end of the 17th century, early 18th century, by Descartes, Leibniz, and Newton. We still study it at school, in high school, because it still works, because it was a great, glorious idea. Think of what that function does. With 2 letters, x, y, and 3 numbers, or 3 parameters, a, b, and c, you notate an infinite number of points. All the points that sit on that curve. That happens to be a parabola, could be an ellipse, an hyperbole, any conic you like. If it is planar, it is 2 variables, x and y, and 3 or 2 coefficients represented by letters. It is an extraordinarily effective data compression technology. With just one little line of script, you notate an infinite number of points. Smart, isn't it? Which is why we still do it, which is why we still learn it, which is why we still use it. But computers don't work that way, because computers having to do the same job will do it the way you see on the right-hand side of my diagram. Computers would not use a function. Computers would make a long list for each point, notating the coordinates, x and y. And that list is long, because no matter how long you make it, it will never be enough. You may notate 1 million points, but at some point you will need another one. When you make it 10 million points, it will never be enough. When you make it 1 gazillion point, 20 trillion, dillion, gazillion, it will never be enough. This is an infinite list that you need, which is not very practical for us because it would take forever. But computers are so fast that they can actually work that way. Not really with 2 billion, trillion, gazillion, but a very long list of a few million points for a computer, which is a very fast machine, is okay. Computers can work that way, and we cannot. We must use calculus because we are slow. So we are so slow, but we are obliged to be smart. Computers are so fast that they can afford to be dumb. Computers don't need to learn calculus because they are so fast that they can do without. They can be stupid because they are very fast. These are two ways of solving the same problems. For us, a short line of code. For the machine, a huge, never-ending list, which for us is a nightmare, but for a computer is a child's game. This is what we cannot do, and computers can do just fine. Now, as we all know, at the beginning, in the 90s, computer-aided design was mostly about making curves, like this one that you see on the screen. And this story has this mythical beginning when Frank Gehry encountered, almost accidentally, software made by our hosts today. And when he realized that to make a big fish, he could use software which was originally designed to make curves on the wing of a fighter jet. It's a long story. You would say, what's the link between a fish and the wing of a... Well, there is a link. It is aerodynamics and hydrodynamics. It has the same name, streamlining. Digital streamlining, in this case, or spline modeling. It was a glorious chapter in the history of architecture. Starting from 1992, it has changed the history of design all over the world, thanks to Frank Gehry and to you, not you in person.
The NURBS. Yes, the NURBS and Katia.
Yeah, spline modeling, Bézier's curves, and NURBS. But this was important. It is already important. It's a history I teach at school because this is the history of architecture from 1992 till today. And it has left remarkable masterpieces around the world. But if you go in some schools of architecture today, like mine and a few others, you will notice that many designers, particularly a younger generation of designers, one generation later, people who are 30 years younger than, or in the case of Frank Gehry, even 60 years younger, you will see that things start to look different. They start to look like that. What you see here is the logic of computation translated into fabrication. A new generation of designers realized that computers really work in a discrete way, point by point. And points, when you print them out, become pixels or voxels. Pixelization, voxelization. And they realized that if computers really work that way in a discrete way, pixel by pixel, voxel by voxel, they might as well show it. Instead of hiding it, let it show. Yeah. Let everyone see what the computer is doing, what the computer is processing. Let's see what's happening inside the belly of a machine. You could hide it, you could cover it, you could streamline it, but at some point, a younger generation of designers decided, let's stop hiding it, let's everyone see what computers really do. If you open the belly of a computer, you don't find a spline, you find pixels and voxels. And things start to look, well, depending on the scale at which you print out, start to look that way. 10 years ago, we called this voxelization, but this style is now spreading. We call it discretization. Things like this, or this, or this. These are filaments, but it is the same logic. Kengo Kuma, the famous Japanese designer, called it particleization, a term which he invented himself, but it basically refers to the same processes. In one case, which I often cite, which is now almost 5 years old, the German, actually Swiss-German designer, Michael Hansmeier, printed out this grotto 5 years ago, and he printed it out using an industrial-grade 3D printer, which he borrowed from a German automobile maker. This grotto, as you see it on the screen, is made of 4 billion voxels. 4 billion voxels, each one a little cube, which was individually notated, calculated, and fabricated. We call this excessive resolution. But excessive for whom? Not excessive for the computer who did it. Excessive for us, because we could not do it. No human could notate, calculate, and fabricate 4 billion voxels one by one. We could, but it would take forever, so we don't do it. Computer can do it because it takes 2 hours. So for them it's practical, for us it is not. It looks weird, it looks wacky, it looks strange, and some find it disquieting for a reason. This is the visible sign of an invisible logic at play. This shows off a way of thinking which is no longer the organic logic of our mind. Only computers can work that way, only computers can think that way. This is the expression of a way of thinking, of a way of processing information which is specific to the machine, which is inconceivable. No, not true. It is conceivable for us, but it is not feasible for us. We understand very well what the computer has done, but we could not do it because if we start today, we would finish in 25 years. So we don't do it. Computer would finish in 2 hours, so they can do it. This is the way computers work. And this is the way computers think, which is very different from the way we think and work. This is us, and this is, well, this is them, and this is us. 2 logics, 2 words, 2 spirits. This is the way computers work, and probably the way we must let them work and think if we want to take advantage of their power. And this could be my last word, unless if you have time to see a couple of movies.
So, thank you. Thank you, Mario, because this is basically at the heart of what we are presenting here. But something we want to go a little bit further. You know, I know by reading on your book, the first book actually I read, The Alphabet and the Algorithm, you come with this particular intriguing situation. It's the designer or the architect facing this situation. This is them, this is me. And how do we organize this new relationship? You know, architects and designers used to have the authority on the design. And suddenly the machine can do different design, but without the architect or the designer. What could be, or what can we imagine in the future in this relationship? Probably something like a third direction. And if I go back to what your exact words, you make this notion of, we used to have architects and designers doing objects, and today they have to go to the objectile, you know, a little bit like a variable. And I would like you to develop that particular...
But the idea that the architect is alone and fully in charge is a modern myth. This idea was invented in the Renaissance by the humanists. One in particular, Leon Battista Alberti.
But we know, we are Milano, so...
It was a group of friends in Florence around the time of Brunelleschi and Alberti, and they decided that they should invent a new authorial way of designing buildings. That the designer of a building should be like the writer of a poem or a philosopher, someone who has an idea and he materializes or has other people materialize it without any change. But this idea, which today we take for granted, which is a myth of modernity, in the Middle Ages, it would have been utterly inconceivable. Architecture existed, but the architects did not. And there are beautiful examples of extraordinary technical expertise built during the Middle Ages, many of them still standing, which is why we still know them and we celebrate them. Gothic Cathedral, the Cathedral of Chartres, still standing up.
Yes, yes, yes.
Who designed it? Nobody did.
We don't know.
Nobody did.
Design.
Many people did working together. It was the collective creation of a whole community, a community animated by faith, who paid for the construction of the cathedral, and a community of craftsmen, artisans, who did not separate intellectual conception and physical production because they did both at the same time. When they started to build the Cathedral of Chartres, they didn't have a design, they didn't have a blueprint.
No, they keep building up.
They had a vague idea of what they wanted. So when they started to dig the foundations, they evidently had a notion that they had 3 naves and 7 bays or something. But even that, they could change because they started with 7 bays and they said, well, shouldn't we add a couple? And then they added, it was a permanent work in progress. When they started to dig the foundation, the plan of the building was determined, but its elevation was not. Nobody knew how tall the 2 towers of the west bow would be. Witness the fact that at Chartres, they are different.
Yeah.
One
And
on
they
the
learn,
right.
they learn as they go. I mean,
Well,
just,
because the team building the tower on the right was, well, the team with the tower on the left was later.
Different, yes.
More technical expertise. So
maybe a different architect too.
there was no architect. There were just
They were-
people. The assignment was build the best tower you can. They didn't tell you make it 70 feet high. They said do as best as you can. And the first was built in 1225. They did the best they could in 1225. The second was built in 1480, and they were smarter. 3 centuries later, they could go up taller. They didn't even think that they should be limited by the notion of making an identical replication of the one already built, because my guess is that they thought that soon a new generation would destroy the old tower, which was too short, and build a new one, even taller, and so on and so forth. The cathedral was a living organism. So long as there was a community willing to pay and artisans capable of building, they would keep building forever. The idea that this is a historical monument, you should freeze it as a Findus fish. And it is. This is an idea that came with Viollet-le-Duc in the 19th century. Historical monument, freeze it, frozen, don't change it or else.
Yeah, okay.
But all this was done by collective cooperation of artisans, of which each had its own skill. Each team could do something. There was a team who could do a molding, another could do the capital, and they worked together in a way that the humanists in the Renaissance couldn't stand and they wouldn't take, because Alberti's idea was, I want that building to be what I have in my mind. I have an idea in my mind. I make a drawing. I put my name.
Annotation.
I put my name on the drawing, my signature. They couldn't make a rubber stamp because they didn't have it. But you put a name, a date, and a stamp. And then you expect the building to be the identical replication of what you drew in plans, elevation, and section. That was Alberti's idea. When he tried to have a building really built that way, he realized that it was impossible. Because the workers, first, they didn't know how to read a drawing. Second, even if they knew how to read a drawing, they didn't care. Because their idea was, well, I have to build an arch. I know how to do it. There was this pathetic example of Alberti who went to see the first building he tried to build. He sent the blueprints to Rimini. Then he didn't want to go to Rimini. It was a godforsaken little place.
Yeah.
He expected the building to be built based on his drawing. When he went to see it, and he saw it, but it didn't look like his drawing. He wrote this pathetic letter saying to the local master builder, the head of the building site, I worked for years to calculate all the proportions. You shouldn't change 1 inch, because if you change 1 inch, you break all the music of the proportion and the harmony of my shapes. But the local builders didn't give a damn about that, because they were used to building what.
But Mario, this is exactly, I mean, this exact thesis that you are proposing, that this pre-Albertian period is exactly what we're going to be living now.
The pre-Albertian is the digital.
We currently have many propositions from, I would say, the new generation of designers, looking at now give away this old fishing, thinking of object back to objective, like open-ended, experimental design, to try to figure out what would be the dialogue with the machine and the computer. So it's not just, I'm here, they are them, let's meet.
Yeah.
Let's having an encounter and redefine maybe what was this kind of fuzzy, yet very rich in creation of new knowledge and know-how from the pre-Albertian period.
By definition, don't like to devolve authorship, because in the modern and modernist tradition, an architect is by definition a control freak. Like in Ayn Rand's The Fountainhead, you remember the story of in the film. If you see a building where your design has been mildly tweaked, you are entitled, as in Ayn Rand's novel, to go and blast it, because it's your creation.
It's your responsibility.
It's your responsibility.
Yes.
But Digital technologies do not work that way. A blueprint works that way, because once printed, you cannot change it. There is your name on it. There is a date and a stamp. It's a legal document. There are liabilities, responsibilities, penalties to pay. You go to jail if you change it after it has been approved. But digital technologies do not work. They can be made to work that way if you try really hard, but the natural spirit of digital technologies is Wikipedia.
But on the opposite, if I'm challenging this idea, does this subject of responsibility that basically lead to the authorship can be given to the machine? You know, or transferred to the machine. What would happen to the attitude of the author or designers today? I'm just like make it up.
Well, if you use parametricism for the way it works, you design a generic object which has parameters. Mm-hmm. So day one, you design a generic system with many parameters, like the equation of a conic, more parameters than that, day one. Day two, you go back into the office, and you could do two ways. You could, assuming it looks like a video game, you could play the video game you designed yourself, or you could devolve it to someone else.
Yes.
Now, normally, if you design a video game, it is not to be the only one to play that game. You would want to invite someone else to play that game. So the normal spirit of parametricism is to invite a second layer of authorship. You design a generic object, and someone else, after you've done it, comes in and plays your game within the parameters you have set. The metaphor is the video game. Someone designs a video game. Then someone else comes to play the game. If you play a game inside a video game, which has already been designed, there are things you cannot change. But then every game is different because you have a certain leeway, and you can choose what you decide. You have a certain amount of free will in each game you play, because each game you play is different from every other game, but within an environment that you cannot change. So the primary author is the designer of the general system. The second one is, in a sense, the interactor, someone who plays inside that game.
Interactor is a very important thing, because you're talking mass customization. It almost comes still from the old era. What about mass interaction? Well, since you know what you will be delivering at the end is just a result of your personal interaction into a dynamic environment. A systemic environment that will be recomposing and assemble and disassemble at any time. Very much at what we see here.
Around 15 years ago, when social media were still new and fashionable and people were fascinated, today people dislike and are afraid of social media because of the things they are doing.
Yeah, sure,
but 15 years ago, when we were brand new, they were the future. We didn't know what would happen. And the mantra at the time was from mass customization to mass collaboration. So use mass customization to invite participatory authorship, which architects traditionally do not like, because they are molded in this frame of mind whereby if someone wants to change your design, you shoot him.
But I think this is changing. You know, we had this exercise we did, an experiment with Patrick Join. He's really this authorship figure in the design in France. Yet he was able to develop with us this great design that is. We started completely in an open-handed blue, vision of what we would be. We were really on this objective, and we interact.
Building information modeling is a vast system that invites participation, but participation limited to technical actors. This is a very technocratic approach. In theory, the future of no one is from IKEA here, right? IKEA, the furniture. There is no one from
IKEA. We know very well IKEA.
There is no one from IKEA here, right? I presume not. But the future of IKEA is not of selling standardized furniture. It is selling a system for mass customization of mass-produced but mass customizable furniture. And in my opinion, just my guess, and I have some inside information, they are working on that.
They do. We know.
So we have the same sources.
We have 5 minutes, and I would like to open up the conversation because I'm asking questions to Mario, but I'm pretty sure there would be some great, interesting insight or question that you may ask to Professor Mario Carpo. Kerenza, I'm sure you would.
Sorry, it's probably just comments, but maybe. One of the things that we've discovered in the last few years is that we've completely turned the profession on its head, because we used to spend hours and days colliding two objects together and trying to make that work, and now that operation happens a million times in seconds, and we have a thousands or an infinite series of solutions. And what do we become in that process? And the second thing is the chance encounter, the chance collision, the chance happen, and where's the a priori in that? How do we, maintain our presence, and then how can we expect the unexpected? Those are things
That's
that
for you.
I know, well, Kerenza from Morphosis Architect, for the people here in the audience. This is actually the dialogue Kerenza and myself are having since we started to build this installation. We don't have the answer. And I think what probably would be is what we will be starting as we do it today. In a way, we are experimenting the balance between, let them doing things, or stop, judge, and try to go back to our slow but maybe continuous and human way of thinking.
At the end of the day, if you use a...
Yes.
Sorry.
No, I wanted just to say is, as you said, is a question of person. It's becoming a human experience again, before anything. It's a great moment. I just don't want to go further.
If you have a parametric system and everything digital is to some extent at some point parametric. If you open the hood and you look at the nuts and bolts, you can dissimulate it, but at the bottom somewhere there is some layer of parametric scripting. And if there is a parametric script which is potentially generative, and it can generate, let's say, 2 gazillion possible little variations of the same generic object, who is going to choose? So if you shift the layer of authorship to that point, there are not many possibilities. Possibility number 1, the primary author decides to take also the role of a secondary author. So first you design a game which has an infinite number of possibilities on day 1. On day 2, you close the machine, you lock it, you freeze, and you say,
so
well...
you recreate iteration.
You go back to... which is, in a sense, frustrating the participatory generative potentialities of a system. This is solution number 1, going back to traditional authorship. Position number 2, you invite a secondary author or interactor, which may even be a cascade, a mise en abîme, or different layer of
it's like
imbricated...
reframing, basically.
Yeah, of
it's
imbricated
reframing
authorship.
the topology.
Yeah. Or you may call artificial intelligence in or a machine, and you ask the machine to try these many variations to optimize them automatically based on some criteria you choose. These are
and I
ways.
may have a completely different one. And I go back to your metaphor, the story, the history of those cathedral builders. You say they have faith.
Oh, yes, I presume so.
So something we have forgotten with this exercise after the this industrial era is we think we can control everything, and we think about performance on a given when there are nothing such a given thing.
Well,
maybe we're here to talk about sustainability. There are no planet B. So if our intention in the dialogue with machine is actually to do a better world, it's that faith, it's that belief that we may do better things than not just staying in this basic question of performance.
Well, but if you go into performance, we have to bear in mind that mass production, economy of scale, and standardization are by definition, by their own technical essence, wasteful. Because they're wasteful.
But this is what I'm saying. I believe that if we believe on something bigger than just that dialogue or that relationship and optimization of that relationship, by looking together into a bigger aim, sustainability, by example, we may find a way.
I never emphasize that point because I think it is self-evident, but for structural designers and architects, it is evident that the modernist way of standardizing structure is by definition wasteful, because in the permanent trade-off between labor, energy, and materials, to save labor, you waste energy and materials.
So maybe you just question performance at all.
Well, but today with digital mass customization, we can focus. Since labor is robotic anyway, so forget about it. You can.
So that may be the solution for designing more sustainably in the future.
It is evident, but
customization
is about optimizing the use of non-reproducible resources, energy, but even more raw materials.
And what about the human resources? They are infinite.
Well, we should economize. We should optimize that, but by not obliging them
to become machine.
Exactly. To do stupid jobs
Actually,
what machines can do.
So we will not oblige architects, designers, or humans to become machine. That may basically wrap up this session. Thank you, Mario. Thank you, Professor Marco, for this lecture. Thank you very much.
Thank you.